This will be the first of several videos in which I give you examples of calculating flux-type integrals. In this one, let S be the portion of the paraboloid z equals 4 minus x squared minus y squared in the first octant, and I want the orientation to be away from the origin. Well, once we draw a picture, we'll see what we mean by that. And let the vector field f be given by x, y, x. Let's find the flux of that vector field through the surface. In other words, let's find the double integral over S of f dotted with big vector ds. So the paraboloid, z equals 4 minus x squared minus y squared, is a downward turn parabola, or paraboloid, which goes up to 4 on the z-axis. So if I drew my axes in, my z-axis would be this way. And I'm going to use a slightly different orientation. I'm going to put my x-axis in this direction and let y go kind of back this way a little bit. Now, before I restrict to being in the first octant, let's think a little bit of strategy about parametrization, and let's also talk about the orientation. So when we parameterize, since z is a function of x and y, one option would be to use rectangular coordinates, so let x equal x, y equals y, and z equals 4 minus x squared minus y squared. I think that what we would see if we did it that way is that the calculations are going to be a little bit more difficult because we're not taking advantage of the fact that this shape has symmetry about the z-axis. So the better way to parameterize is going to be to adapt cylindrical coordinates. So just make a mental note that we're going to use cylindrical coordinates when we parameterize. Also, before I restrict, let's think about what I mean by the outward normal vector. I said that I want it oriented away from the origin. If I'm at any point on this surface, there are going to be two unit normal vectors. At this point, one of the unit normal vectors would point up and outwards from the surface, and the other one would point inward and down. So these are both vectors with length 1, and they're pointing in opposite directions like this. Here I want the one which is oriented away from the origin, so I'm choosing the blue vector here. So I'm going to erase this one. So when I indicate the orientation of a surface, sometimes I do that just by drawing a little arrow on here. Now let's make the restriction that the paraboloid needs to live just in the first octant. The first octant is where the x, y, and z coordinates are all positive. So if I slice with the xz plane, I get kind of half of a parabola coming down and meeting at this point. So all of this is gone. And kind of the same thing happens back here on the y-axis. So in the back, I've got that. So I have this strip there, if that makes sense. So kind of a sail-shaped piece. It'll be 1/4 of that paraboloid that I drew before. Of course, the way that we'll restrict it being just in the first octant is by putting restrictions on the parameters. So now, our first step in solving this problem is going to be to parameterize this surface S. So let me just make a note down here about what my vector field is. F of x, y, and z is equal to x, y, x, and my surface is z equals 4 minus x squared minus y squared. With those notes, I can erase everything over here. All right. Step 1 is to parameterize. So remember, what we're parameterizing is the surface. When you carry out the parameterization, it has nothing to do with the vector field at all, just the surface. And as I said, we're going to use adapted cylindrical coordinates to carry out this parameterization. So in our thought bubble, we're we're letting x equal r cosine theta, y equal r sine theta, and z equals z. We substitute those into the formula. Z equals 4 minus x squared minus y squared. Notice I can rewrite z equals 4 minus x squared minus y squared as z equals 4 minus x squared plus y squared. And the reason I do that is I know that x squared plus y squared is equal to r squared. So z is the same as 4 minus r squared. I substitute that back in for z, and I get x equals r cosine theta, y equals r sine theta, and z equals 4 minus r squared. So let's capture that down here as our parameterization. X equals r cosine theta, y is r sine theta, and z is 4 minus r squared. So that's my parameterization. Written in phi form, phi of r and theta is equal to r cosine theta, r sine theta. I didn't leave enough room. Phi of r and theta is r cosine theta, r sine theta, and 4 minus r squared. Now let's think about the restrictions we need to make so that we stay in the first octant. Now since theta measures the angle away from the positive x-axis, I can see that theta is going to start at 0, which puts me on the x-axis, and swing out to pi over 2, which will take me to the y-axis, and go no farther. So for theta, I'm going from 0 to pi over 2. Now thinking about r, I want to start at a radius of 0, which would be on the z-axis, and stop when I get to the xy plane. Well, remember the xy plane is when z equals 0. So here's the equation of the paraboloid, z equals 4 minus r squared. So if I intersect that with the xy plane, which is z equals 0, then I get that 4 minus r squared is 0, which means that r squared is 4, so r is 2. So this circle in the xy plane has radius 2. So later on, when I set up my bounds, I'll have r going from 0 to 2 and theta going from 0 to pi over 2. So that's the end of step 1. Step 2 is going to be to find big vector ds, which is plus or minus d phi dr crossed with d phi d theta, dr d theta. So let's calculate some partial derivatives. D phi dr is equal to cosine theta, sine theta, negative 2r, and d phi d theta is equal to negative r sine theta, r cosine theta, and 0. I think I can fit the cross product down here. D phi dr crossed with d phi d theta, I can find by taking the determinant of this matrix if I put I, j, k on top. So it would be I times 0 minus a negative is plus 2r squared cosine theta, minus j times this determinant, which will be 2r squared sine theta, plus k times this determinant, which is r times cosine squared theta, plus r times sine squared theta, which is just r. So bringing this back to the top, big vector ds is going to be plus or minus 2r squared cosine theta, comma 2r squared sine theta, comma r dr d theta. So how do we choose? How do we choose whether it's going to be a plus or a minus? Notice that at all of the vectors on this portion of the paraboloid, the z component is positive because this vector is pointing above horizontal. If it had a z component of 0, it would be pointing horizontally. But since it's above the x-axis, it has to be above. The z coordinate has to be positive. So notice that the z component here is r, and r is taking on positive values. So that means that I need a plus sign in front. So vector ds is going to be positive this. And I'll continue this problem in the next video.